Awesome. Thank you so much. Well, thanks, folks, for having me. Appreciate you making the time. So I am John De Havilland. I am a customer success director here at Microsoft, working with a large number of customers, talking about artificial intelligence, machine learning, and some other interesting topics. I want to spend a little bit of time today just sharing some knowledge about artificial intelligence and machine learning, talking a little bit about what it does, and have some interesting examples to show you too. So we've got a fairly small audience here today, so we can keep this interactive. If you have questions, feel free to interrupt, or if you want to put it in the chat, you can do that. I have it open here, so if you want to have questions or want to ask anything, then feel free to interrupt me. You can either come off mute or put a question in the chat. I'm keeping an eye on it here. And yeah, I'd say let's start. So I've got a few slides I'm going to walk through, just to kind of lay out what machine learning is, maybe give you an introduction to how easy it really is to be able to kind of get started in machine learning. So singularity, the term singularity really describes a moment when civilization changes so much that its rules and technologies become incomprehensible to the previous generations. And we can think of this as sort of a point of no return. And so when we talk about artificial intelligence, a lot of people really think we're getting to a point where a singularity event is happening. And it's beginning when we can really no longer understand what computers are doing. And it's super interesting to say that we're on this kind of tipping point right now. But artificial intelligence has actually been around for a fair few number of years. So does anybody want to posit a guess of when did the term artificial intelligence first get talked about? When did artificial intelligence come about? Does anyone want to have a guess at a year?
I'm not really sure when, but I do know that it's like it's used in so many like common items now, like with Siri, Alexa, and stuff like that. Those all utilize artificial intelligence.
Mm-hmm. Exactly. So do you think it first came about in the 2000s?
Yeah, I would say, yeah, maybe early 2000s. I think that's about accurate.
I like it. I like it. So what if I told you that actually the first time artificial intelligence really came about was a lot earlier than that? A gentleman called John McCarthy first coined this term back in 1950. So in the mid-50s, John McCarthy basically defined artificial intelligence as the science and engineering of making intelligent machines. It's a lot older than people think, and a lot more has gone into it than people realize. When we look at the timeline of where artificial intelligence began and where it started, if we take a step back, back in 1877, we had our first calculator. AT&T back in 1939 created a very rudimentary artificial intelligence system. There was a robot created that leveraged basic artificial intelligence in 1969. We had voice recognition in 1992, so the things that are powering platforms like Siri using voice recognition, the first one was back in 1992. And we actually had our first self-driving car back in 1994. So it has been around for a lot longer than people realize. What has changed, though, and why artificial intelligence is now a lot more common and ubiquitous is two things. One, we have a lot more data. So a large number of people are collecting a large amount of data. And in order to train artificial intelligence systems, you need a lot of data to make them accurate. But then on top of that, in order to be able to train these systems, you need a lot of computing power to do that. And the era of the cloud has really shepherded in the ability for artificial intelligence to be trained at scale. So the combination of cloud computing and the collection of large amounts of data have accelerated this revolution, hence why you're seeing all these developments like you talked about. But a lot of people don't realize that a lot of the work done to get to that point happened a lot earlier. So some of you may have heard of the Industrial Revolution, and this was a concept and a revolution that really basically automated manual work. We're living or kind of lived through the information revolution with the age of computers and service workers, and this automated mental work. And we are right now living in the AI revolution, and the AI revolution is all about automating automation itself. So we're at a point where we're now being able to kind of use AI to automate tasks that we were previously looking to automate through other means. So what is machine learning all about? So I guess before I dig in and walk through kind of the basics of machine learning, how many folks here on the call know anything about machine learning, have done anything or read anything about it to understand how it works? All right, so I will take silence as this everyone's kind of fairly new to this topic, which is good. So we'll kind of keep this at a fairly high level. But at its core, machine learning essentially is like having a radar that sees into the future. If you give a machine learning algorithm enough data, it's going to be able to solve and repeat solving for problems over and over again. And the power of it is you just need to be able to provide it data and train it to understand how to interpret patterns in that data, and then be able to use the information about those patterns to then answer questions about the data and new data that you have. But if we want to make machine learning simple, it's not as complex as people will have you believe. There are essentially 5 fundamental questions that machine learning can answer. So I'm going to walk through these questions. When you think about this, or any machine learning problem, think about it in the guise of these questions, and you'll understand what type of machine learning can be used. And if the problem doesn't fit into these questions, then maybe machine learning isn't the solution for what you're trying to do. But essentially, there's these 5 questions. First one is this A or B? So does this image have a cat or a dog in it? Classification, that's a pretty common use case used in a lot of machine learning problems, but essentially it's classifying whether something fits into one category or another. The next question is this weird? So, a canonical example of this would be somebody makes a purchase using your credit card. Does that look out of place versus all of the other purchases that you've done? Detecting an anomaly in the behavior and based on prior data. So is this weird? The other piece is how much or how many. So this is basically predicting a number. What is the price of this house? This is a regression problem. So classification, anomaly detection, you've got regression. So essentially the question is, how are you trying to predict a value? Another question that machine learning can answer is, how is this organized? How are groups of people related somehow? How is their behavior tied to patterns in the group? So this is all around clustering, to cluster groups of people together. To say, an example could be people who like this type of movie fall in this type of group. They could be people who own Volvos like Marvel movies, for example. Now, machine learning can look at data and discern patterns around that to say, we know people who own Volvos and have dogs as a pet like Marvel movies, and so maybe we should target advertising for the next new Marvel movie to that group of people. And then the final question that machine learning really can answer is, what should I do next? And this is really common in things like self-driving cars. I come to a stop sign and I need to make a decision. Do I go left, do I go right, or do I go straight? And this gets reinforced as you move down a path. And so this is kind of being able to answer, what is the next sequence of events that I need to do? So let's just think about machine learning and what do we mean by output? So we're going to we train a machine learning model, we pass in some new data to it, and we get some output from it. What does that really mean, and how do we get to that point? So let's take a really simple example. So here's a sentence. I just ate a big lunch and I am feeling sleepy. I'm going to take something. And let's say we pass this sentence into a machine learning model. It's been trained to understand the sentences, and it's going to give me what the next word is going to be, the output. So let me ask the group here, what would you say the next word could be here?
Nap.
Excellent. So nap could be certainly the next word. How confident are you, percentage-wise, that it's nap? Would you say you're 100% confident that it's nap?
Probably pretty confident. Maybe like in the 90s.
Okay, so you're like 95% confident it's going to be nap. But what if we change the sentence slightly and just said, I just ate a big lunch. I'm going to take a. Now, are you still 95% confident the word is nap here?
No, it could also be like walk.
Right. So this is where it gets tricky. And so at its core, machine learning is all about providing outputs and a percentage weight on those outputs. So in this example, in the first statement, you felt that you were 95% confident that nap was the word. So in a machine learning model, it would look at that and maybe it would say, agree based on prior data that it knows about sentences that nap is the word, and may say it's 95% confident that nap's the word. Because of the context of the prior sentence, it made sense and the percentage was fairly high. But then in this one, there's less context. And so, your percentage reduced. You'll say maybe 80% confident that it's nap. And so the machine learning algorithm, depending on the data it's been trained on, probably would have a lower percentage too. And so the outputs are essentially a weighted value to say we're this confident that it's this value. And the higher the percentage, the more confident it is. But it's unlikely that it's going to ever be 100% confident. So that leads us into the realm of saying, well, when we're using machine learning to make decisions, it's never 100% confident in the decision it's predicting. So depending on the use case, that could matter a lot. So in this case, it's not a huge deal. And so maybe, we look at this and the machine learning algorithm says nap is 88%, walk is 7%, call is 3%, and test is 2%. Maybe then we use this to say, well, anything over 80% we'll go with, because 20%, 80% confidence is pretty good. We don't mind if it's 20% off. So we'll take anything over 80%. And so you could certainly put a threshold to say, if it's over 80%, we'll take the value the machine learning algorithm outputted. But what if this was a different model? What if this was a model to decide the next step in a surgery the surgeon was going to make, and then telling you that it was 80% confident this was the next surgery? Would you be so confident to have that threshold at just 80%? Or would you want it to be higher?
We'd want it to be higher.
Right, exactly. So a lot of these things all depend on what you're trying to use the machine learning models for, but none of them are ever going to be giving you 100% accurate results. They're all a percentage and based on prior historical data. So that just, it kind of talks about the outputs you're getting. You're basically getting a prediction that's got a percentage confidence of how sure it is of that prediction based on the prior data. And then you as a human have to make determinations on what your threshold of tolerance of risk for that is. If it was 50%, that's pretty much basically saying it's no better than guessing. And so at that point, how good is that machine learning algorithm? So when we talk about machine learning, there's a bunch of different ways to think about it. You often hear of neural networks, though, and neural networks are super powerful. They're revolutionizing where we're at with machine learning today. When you think of Siri, or you think of image recognition or translation, all of those are powered by neural networks. And the advances we've seen in most of the recent adoptions of AI have all been driven through advanced neural networks. So there's traditional machine learning, and then there's neural networks. Traditional machine learning has been around for many years, and that's a lot of the stuff that came out of the 50s and 60s, and the stuff that was used in the early 90s. And then neural networks are a little bit newer, but their evolution was built on some of the work done for traditional networks. But at the same time, neural networks are providing a lot more power. And the reason for this is simple. At its core, this is how traditional learning models look at data and how they perform. And what you notice here on this graph is, as you give a traditional algorithm more data, at some point the performance doesn't get any better. It plateaus pretty quickly. But the same is not true for neural networks. The more data you give neural networks, the better they get, and the better their performance is going to be. So what is a neural network? So I'm going to share with you kind of some of the basics of a neural network so you can understand that it's not as complex as it may seem. Now, obviously, you can certainly go really complex with these, but at its core, building a neural network and understanding how it works is fairly straightforward. It's called a neural network because it's based to some degree on how neurons work in the brain. And this is a fancy picture of a neuron here. But in order to demonstrate kind of how a neural network works, let's walk through an example here. So let's say you're the proud owner of this car here, and you would like to sell it, and you're trying to figure out, well, what price should I put it on the market for? So when you're trying to figure out the price for this car, what sort of characteristics would you think matter in determining what price you'd want to put the car at? Anyone want to have a guess?
How old it is.
Okay, so the age of the car. How well it runs. Cool. Do you think the color would affect the price? What about miles per gallon? Model, right? There's a bunch of different things, a bunch of different characteristics. Interesting you mentioned how old it is. So, we've got a few different characteristics here, and we want to use these to get to the price. So we've got age, we have color, we've got miles per gallon, we've got model, and we essentially want to use those characteristics to get to the price. And so I guess you mentioned age. So in that case, if it's an old car, like if it's significantly older, you would say the price is lower, I would assume, right?
Yeah.
And then if it's a different color, the price could be, depending if it's a bright orange car, maybe it won't sell as much as a white car, so price could be lower. So you make determinations based on a few of these categories. Now, essentially, all that neural networks are doing, and machine learning in general is doing, is just taking this list of properties and just expanding it out. There's many different other properties that could also apply. And as a human, there's only so many that you're going to really factor in, but a machine learning algorithm can take in many more properties and use those to also determine the price. But then it also gets tricky because these individual properties also could change. And just because something's old doesn't necessarily mean the price will be lower. Because what if the car was this? This may actually be more expensive, but it's a lot older. So age at some point then may affect the price in a different way. And so there's a lot of variables to all of these different properties. And so essentially the way machine learning and neural networks are working is making it easier to kind of look at many pieces of data to get to the price. So if we just use this example of these 4 properties, a neural network essentially all it's going to do is take a bunch of historical data that we know. So it'll have a bunch, you'll collect a bunch of past cars with these pieces of information about them and known prices that they sold for. And then what a machine learning algorithm will do and a neural network will do is essentially automate the process of taking all of those properties, simply applying different weights to them to get as close to that price as possible. And it will do it for each piece of data, each car that you have in the system. So what it'll do is for the first car that you have in your piece of historical data, it'll take the age property, it'll apply some different weights, and then also do the same for color, do the same for miles per gallon, same for model, apply just different weights to the numbers and values for these, and then essentially try and get as close to this as possible. And it will do it for all of the examples in your historical data. And the output from the neural network will be a trained model that will have the weights based on your historical data that it feels get to the closest to the prices. And then when you pass in new data that it hasn't seen before for your car, it'll give you a price that it predicts will be the price you should put it for. That's all it's really doing. So essentially, it's going to basically take these weights, apply them to get close to the price, do it across all these properties. And you can imagine there's a million other properties you could use. And as a human, that's like if you were trying to do this manually, that'll be a lot of effort. So that's where the power of a neural network comes in, because it's automating all this for you. It's taking all these properties, trying many different weights to learn how to get to that price. And when it's figured out the best weights to use, it stores those in the model. So any new piece of data, it'll use those weights against that data to create the next new price. Now, this is a predicted price, so there's no guarantee, and there'll be a percentage confidence on it, but it gives you an idea. So that's where the more data you have to train it, the more realistic those weights will be. So I'll pause there to see if there's any questions on, see if that makes sense.
So I have a question. We're saying that it could, like, a car that's older than like a certain age would like be rated like more expensive. So like, would it be able to like create like a line that says like, okay, cars past like cars earlier than like the 1970s are like more expensive? Like, would it be able to like tell?
Yes, it would. So you'd have to have that sort of data in your set of training data, the historical data. So you'd had examples of cars older than the 1970s that maybe cost a certain amount. But as long as you have those in there, whenever it's creating these weights, it's going to use the weights that make the most sense to get to those values. And so it will definitely take those into account. And the more examples you have of both older and newer cars, the more accurate it'll be.
That's pretty cool. Thank you.
No problem. So, shared with you kind of the 5 basic questions of machine learning and walk you through a very simple example of under the hood how a neural network works. And it's not any more complicated than that. Essentially, the only thing that makes it more complex is bigger data, more complexity in terms of how many layers. But at the core, that's all it's really doing. So now that you have enough information to understand how these are put together, I'm going to walk you through some really interesting examples of how recurrent neural networks are performing very well. There was a paper written called The Unreasonable Effectiveness of Recurrent Neural Networks. And this is, as I said before, this is what's fueling the advances in AI today. And some of the most advanced features you're seeing are driven through neural networks. And they can do some really powerful things. So I have some really interesting examples here that I want to walk you through to showcase what I mean by powerful. So I'll give you a minute. Take a look at this. This is a clip from a passage from a book. And I'd like you to like someone to have a guess and say who do you think the author of this would be? Anybody have an idea who might have written this? I like it. So Shakespeare certainly is a really reasonable guess. And when I first thought this, I thought the same thing. But what if I told you that no human wrote this, that an artificial intelligence algorithm created this? They took an artificial intelligence algorithm, they trained it with the entire works of Shakespeare to understand how Shakespeare wrote his plays, and then use that to create new plays. And so this is what you're seeing here. This is an output from an AI algorithm trained across the entire work of Shakespeare. So hence, it looks and feels like Shakespeare, but it's something new that he did not himself write. So in terms of breakthroughs using neural networks, vision has been around and being able to identify objects in things for a few years now, and it's super effective. In fact, this graph here on this slide shows that in 2015, we were able to finally achieve better than human accuracy in recognizing objects and images. So in 2015, a neural network was trained that performed better than you or I could in terms of looking at an image and identifying the object in that image. So if you think about the opening statement around entering a singularity at this point and not understanding what computers can do, they are now achieving more and more advances versus what we're able to do in certain fields. And so that's pretty compelling. This is that neural network that was trained for that. And as you can see, it's just many, many, many layers. So if you think about the car example we walked through, that had a single layer. This is taking that to, I think there's 152 layers here on this one. But at the same time, it's doing very similar things to what the car example did, just at bigger scale. Similarly, we achieved in 2017 better than human error detection in transcription. So listening to audio and transcribing it and recognizing words in that, and AI algorithms started to perform better than humans. And similarly, even more impressive, in 2016, an AI algorithm surpassed the ability for humans to comprehend text and answer questions on it. And this is harder than you might think, because really it's essentially saying you read a passage of text and answer a question about it. So you have to understand the context, full context of what you're reading, and a machine learning algorithm was able to perform better than humans at that. So a lot of advances with neural networks and driving a lot of great progress in this field. So here's a set of photos, and using a trained neural network, it's been able to colorize these photos, and it's pretty powerful. And if you look at these actually look really cool. In terms of how this works, it's kind of interesting. You train a model, basically pass it a bunch of black and white photos and pass it in the colorized version of it, and it learns how to convert those. Interestingly, though, you run into some unique edge cases here. So if you look at the top one, we have the input, which is this rack of candies or chips, I guess it's candies in a supermarket. The middle image is what it actually should be, but if you look at the output there, it's pretty faded in terms of its colors. And that's because there's just way too many colors going on. And so this doesn't perform so well if the color contrast isn't there. And then really interestingly, in the bottom one, it does really well colorizing the image, but it thought you had an orange tint instead of a blue tint, which if you think about it, it's got to be super hard for the AI algorithm to really determine what color that tint should be, but it's at least colorized it in the right way, separate from the surrounding elements. And so that's based on some of the data that's been trained on. Now, a bunch of these powerful examples are all about images, and so you may be scratching your head to say, well, John, how can we go from talking about price of a car to how does the machine do the same with an image? And at its core, it's still the same concept. You're still trying to apply and figure out the right weights to apply to properties. And when we look at an image, we see the picture of these dogs, but a computer will just see numbers for the pixels. And so based on the type of image, these could be the weights to say what is the color at each of those pixels. And when we zoom out of that and look at it in the bigger picture here, we as a human perceive it as a collection of pixels and makeup, and we see dogs. But at the same time, a computer is going to see different values for each of the dots on that. If we look at a super simple example, if you're doing handwriting recognition, we have a number 8 over here. Imagine this is a grid of 28 by 28, so 784 pixels. There'll essentially be values for each one of those pixels. And you can see where when the 8 is written, those values change, and this is going to be various degrees of black or white to make up the image, and you can kind of basically see where the image is drawn. But a computer's seeing these as numbers. If you then take each of those pixels, all 784 pixels, imagine those are the properties. The neural network will essentially just apply weights to each of these to figure out how to get the values. The values here are the outputs. So it's going to try and learn based on a bunch of images how to get these outputs and get to a label, which would be 8. So that what you're trying to figure out is the weight to get to number 8 over here. And then it's going to learn anytime it sees an image with those sort of values that it's going to be an 8. But it's not that much different from the car example we walked through before. These are, instead of those being age, color, MPG, these are just pixels, right? It's the same concept. So here's an image. Anybody want to have a guess what city in Europe this image is from? Anybody have any idea where this might be? Well, what if I told you this wasn't even a city, and what if I told you this wasn't a real photograph, and that this was a photograph generated by an artificial intelligence algorithm that had learned how to generate its own photographs? So this is getting to a point where AI is powerful enough to create images that if you don't look at them carefully, they can be passed as real. Another interesting and maybe more pertinent example, this is President Barack Obama, and he's giving a speech. This is not, right? This is actually footage that's generated using artificial intelligence algorithms to create a synthetic Obama, learning how to mimic his face and lips and being able to generate it. So we're at a point where AI could also be used to generate things that appear real without scrutiny, and certainly could be challenging. On a more lighter note, though, a company wanted to harness this power of artificial intelligence, and they thought they're going to create a business to generate motivational posters. And they thought, we're going to train the model to learn a bunch of motivational phrases, take a bunch of really cool photographs, and generate these posters. And they created this model. It seemed to be good. They trained it. It was working pretty well. They released it. And then people started asking for refunds because the posters that were getting generated didn't come out quite how they thought. They were getting posters like this, for example, which I guess you could say is motivating to some degree, but it wasn't quite what they were going for. So while there are certain advantages, there's also a lot of challenges with AI today where without humans in the loop, it doesn't necessarily always produce the results you're expecting. Now, this is a really fun and also quite compelling example. So who here thinks they could be good at lip reading? Has anyone tried to read anyone's lips? All right, so this is going to be a little tricky because we're virtual, but at the same time, there's going to be an example coming up to say, can you read this person's lips? So let's give it a shot. So does anyone want to have a guess at what this person was saying? Yes, could be good.
I thought that she was saying what?
All right.
I thought she was saying watermelon.
I like it. It's tough. It's super tough. So let's take a look. So the sentence she is saying is place blue in M1 soon. Nobody would have guessed her saying that. But they trained a neural network, LipNet, to be able to understand and read people's lips. And that's what you're seeing here. And it does it with significant accuracy. As you can see, it correctly predicts what you're saying. And so this is super powerful in terms of the use cases you might want to use it for, in terms of people being able to use it, but it's also kind of scary as well to some degree. But the fact that it's able to understand and read someone's lips is super compelling. Now, recently, there was even more advances. So has anyone here heard of GPT-3? So let me pull this up and show you, because this is super cool. So GPT-3 is an algorithm trained by OpenAI in conjunction with Microsoft on massive corpus of text. Essentially, millions and millions of documents were used to train it, and it can do some really, really powerful things. And there's a website that's got a bunch of examples of this, which I'm going to pull up over here. You can go check this out as well. But essentially, it's a language model, and interestingly, not anybody can go use this. Like, in terms of signing up for it, it's so powerful, they have restricted access to it because it can generate very realistic documents. It can generate like realistic code and applications. So if we take a look down here, there's a few examples, right? And I'll just highlight some of these. So words to websites. So if we jump into this essentially uses, so using GPT-3, you can essentially describe what you want the website to be, and it will go and create the code for you and the website for you. So essentially, I think this guy, let's see if it shows it here. So here, for example, he basically wrote the sentence, a website like apple.com for Twitter, and it created this, which is super powerful. And it created the HTML for it and the images. There's a bunch of other interesting examples. I'm not going to go through them all, but you can use it to generate blog posts or writing or news articles. You can create creative fiction with it. And essentially, you just give it an example or seed, and then it'll go and generate those for you. There's even a recipe generator. So if we take a look at the recipe generator over here, it goes through and basically creates recipes for you. Given a couple of ingredients, it'll go generate the recipes for you. So super powerful, and it's going to change how we think about AI in the future. But this is fairly new advancement. Resume generator, so if you want to generate a resume, it seems to be able to do that. It's kind of cool. So people have built some of these examples, and he describes it here, and it goes ahead and generates a proper resume formatted for you and everything, which is pretty cool. If we fast forward to this, it's going to go and generate the resume in the right format. So I think it's super cool. So those were just some examples of the power of recurrent neural networks and the way they're changing how we think about doing things. So in the last kind of 15 minutes or so here, I want to just touch on another challenging area, bias in AI. And this is definitely something to think about, especially if you're working in machine learning. It's a challenge that's becoming more problematic in terms of the data that we're using to train our models has inherent bias in it. That's causing challenges in terms of how it's then used to make decisions, right? If you're training a bunch of machine learning model to make important decisions, and the data you're passing in has certain biases inherent in it, then that's just going to get repeated and then potentially amplified too, because AI is taking that and then amplifying that at scale. And I'll talk through a couple of examples of where this could be a challenge. But when we think about just a simple challenge with AI, vision detection, we look at this and we go, okay, well, this is a cat. And it does really well. We look at it and go, yep, this is a cat. And then it says, it even describes that it's a close-up of a cat, which it certainly is. Then we show it another cat, and it says, this is not just a cat, this is a lion lying in the grass. So it's not only able to detect that it's a cat, but it also knows this is a lion, it's different from the other cat, and it's able to kind of describe that pretty well. Now, interestingly, there was an experiment done where they were using and training a model to be able to detect the difference between huskies and wolves in a algorithm. And they were going through looking at the images, and this one image came. When they trained it, it was doing reasonably well, but they kept passing in. They passed in this image, and it would come back and say, "Well, this is a wolf," and yet it wasn't. It was a dog, and they were like, "Well, why is it thinking this is a wolf?" And it was doing okay everywhere else. And this is where it gets challenging with machine learning with AI, is because how is it making the decision that that it thinks this is a wolf, or how is it making a decision that it's a dog, right? And so I guess I'll ask the question here to the group, like, if you were looking at this, what would you use to determine, like, how would you know, like, if you're looking at this, like, what sort of things do you think it might be using? What characteristics of the dog here do you think it would be trying to look at?
I think it might like actually be looking at like the characteristics of the dog, but like it might not be looking at like the chain that like that's leashing it, which probably wouldn't be there in a wolf.
That's a good point. Now, when they looked at this, they actually did some analysis to figure out, well, how was it saying, why was it saying this was a wolf and not? And they actually realized that it was making the decision between a dog and a wolf, nothing to do with the image of the dog at all. And in fact, it was deciding it purely based on whether there was snow in the picture or not. And so this was an interesting eye-opener for the people, the researchers looking at this, because they're like, this machine learning algorithm was making decisions and seeming to perform well, but the decisions it was making was simply whether there was snow in the background or not, nothing to do with the fact that the dog has a chain or doesn't have a chain. And so by not understanding what AI is doing makes it dangerous. And there's a really great quote here that the greatest danger of artificial intelligence is that people conclude too early that they understand it. So there was some other interesting research here talking about the bias in AI. You know, if we back up for a minute, there's this concept of word embeddings, which are often trained on billions of words from the internet or wherever, and they're super popular to be able to kind of create things like chatbots, or when Siri responds back to you, it'd be able to kind of interact with people or even do additional things. And one of the really cool things you can use this sort of technology for, training a neural network to understand word embeddings, is to do analogies. And it could answer questions like, what is the female equivalent of a man? And in this case, that's a woman. So by training it on a bunch of different pieces of text, it learns that the female equivalent of a man is a woman, which is great. And the folks at Microsoft Research were actually looking at this, and they were going through this, and they were like, okay, well, man to woman, and then king. This makes sense. We look at the data, and then queen. And so this is really good and really powerful. It's doing the analogies, and it's giving us what we need. But then, to their horror, they passed in doctor. And what do you think the answer came back out as?
Patient.
So it's good. That's a good answer. I like that. But it didn't. It actually came back and said nurse, which was super concerning, because based on the data, it had learned that the female equivalent of a doctor is a nurse, which is just reinforcing sexism from the data that has been there before. And so this is where it gets really challenging. And when we talk about bias in AI, this is a perfect example of that, because the female equivalent of a doctor isn't really a nurse, right? The female could be a doctor, the doctor could be a female. There's nothing to say you couldn't. But the fact that if this algorithm is looking at the data, and based on maybe things from the data that were older and had these biases, it's generating things that are reinforcing those. So it's just something that, if you're ever working with machine learning, just understand the data you have, and the fact that anything you pass into a machine learning model or an AI model is just going to get amplified. And so if the data is bad or the data is biased, those biases are just going to be perpetuated throughout the data and the models that you have. And so I'll leave you with this final quote from Cathy O'Neil in her book, Weapons of Math Destruction: How Big Data Increases Inequality and Threatens Democracy, which is a highly recommended book. When we blithely train algorithms on historical data, to a large extent, we're setting ourselves up to merely repeat the past. And I think that's definitely something we need to think about. So that kind of covers just a high-level intro to ML. I'll open up, see if anyone has any questions.
Wasn't there also like a study where a facial recognition software wasn't able to equally detect faces of different races or ethnicities?
Yeah, I believe there was. There's been some challenges from what I've seen around that too. There's a bunch of examples where definitely machine learning algorithms have been trained with data sets that have certain biases. So in that case, I think the data sets maybe only had a significant number of Caucasian faces in them, and so performed badly when trying to identify people who weren't Caucasian. And so that's just bias in the training sets. And so there's a lot of work going on right now to make sure any of these, especially more wider used trained algorithms, have the right level of data in them to make sure that they're able to perform without these biases. But it's a huge problem. It's a huge problem across the ecosystem because in order to push these advances forward, people push data in and we're really excited with the results. And now we're starting to think about it and think about things like the ethics and the biases that are inherent in that, which is definitely a trending area. Cool. Well, hopefully you found this useful. I know it was super high level, but we went through a bunch of different stuff. Hopefully it gives you a flavor of the fact that AI is making huge advances, that it's not as complex as people make it out to be. And it's definitely an area of generating a lot of excitement.